23.
I guess it's also.
Okay, let's get this show on the road. We can hear you. That's always good. Okay, welcome to this latest version of fluid mechanics. Again, if you have questions, chat. Questions are acceptable, or if you have the nerve, unmute yourself and break in. We'll try to handle questions as they come up. In this case, for the next few lectures today, right into next week, you should have the handout that I circulated almost 2 lectures ago, and it has the Moody diagram and different relationships, so I'm just showing you this. It is posted in Canvas underneath your handouts, so that will be good to have because we'll be using it a lot. And again, I've turned on transcription. That doesn't necessarily mean it's an accurate transcription. Evidently, last time the Moody diagram translated to the Booty diagram, and I can't help it, but that's the way it's going to come up. So, what we're continuing to talk about is the pressurized pipe systems and how we use these ultimately for design and analysis. So what is pressurized pipe flow? The fluid entirely fills the cross-section. You can certainly have a big pipe like a culvert and the fluid doesn't fill the cross-section. In that case, the constructs we're using for energy losses and some of the other aspects don't fit because that's not pressurized pipe flow. So in this case, you have the fluid entirely filling the cross-section. And what that means is the no-slip condition is operating over the entire cross-section, and it operates over the inside diameter. That's really important. The ID ultimately is the diameter we use in all of these equations. When you hear something like 6-inch diameter pipe, that's not usually the inside diameter. That's the nominal size, or what we call it, the name, nominal. And in another lecture, I'll be giving you the different types of materials and the different types of inside diameters so you can understand that a little bit better. But that's actually what's used, inside diameter. In this class, if you're told you have a 7-inch diameter pipe, assume that's the inside diameter. As the fluid moves inside the pipe, friction losses therefore continuously occur, all because of the no-slip condition creating a boundary layer. And the energy grade line, or the hydraulic grade line, may be above or below the pipe. Just because it's pressurized, a negative pressure is a pressure. A vacuum is a pressure. So just understand that. We've drawn a few scenarios where the energy and the hydraulic grade lines are below the pipe. There's nothing wrong with that. It can certainly physically happen. The most important aspect in pressurized pipe flow, or what's known as closed conduit flow, is that the fluid is completely filling the cross-section. So again, you can certainly have laminar, transition, and turbulent boundary layers in the system. There's no real, most often, leading edge or trailing edge. It's just that you have an established boundary layer throughout the piping system. So what we started off with last time was looking at some parallel plates and ultimately extending this to a closed conduit. And the parallel plates are convenient to look at as a start, and we're going to have fluid moving between them, but basically it's infinitely wide, and it makes for just a simpler analysis. And what we did on this was identify the forces that were acting, and we were applying to this little differential element, dl by dy in size, and remember we had to skew the coordinate axis systems in order to have the L dimension parallel with the directional flow, basically. And we recognized that when we included the momentum flux terms, that because we had a constant thickness between these two elements, these two flat plates, and we were looking at a constant element size, that the momentum flux leaving equaled the momentum flux leaving, entering and leaving were the same, and therefore the right-hand side of the momentum equation was zero, and therefore the sum of the forces will be zero. So then we started looking at the forces. There's a pressure force on each side, because we cut the element away from the rest of the system, and that's how it knows the rest of the system is there. Are there pressure forces on the top and the bottom? Of course, but they're in the y dimension, and we were only looking at the L dimension. We also had shear stress on the top and the bottom, which could be integrated into forces, and we also had a weight that was acting down the plane of the L dimension. And so we could substitute all of those pieces into the equation up above. Sum of the forces equals zero. And what we arrived at was, interestingly, was that P over gamma plus Z is changing in the L direction because we have the velocity profile. What caused the velocity profile? The no-slip condition. So the velocity profile is dictated by the type of boundary layer you have. Is it laminar, transition, or turbulent? That then dictates the amount of shear stress and energy losses. But the most interesting thing is we have energy losses now, and the energy losses come out of a hydraulic grade line. That's what's really important. The magnitude of the energy losses are related to the kinetic energy, V squared over 2J. But they are taken, stolen from potential energy. That's a really important point for you to remember. So again, the no-slip condition created the boundary layer, and the boundary layer gave us the velocity profile, and once we have the velocity profile, we have shear stresses, and once we have shear stresses, we have energy losses, which is following. Before, once we got the shear stresses in the last 2 weeks, we were looking at the drag force. We're basically looking at the same consequence of the velocity profile in the no-slip condition, and therefore the boundary layer, but now we're looking at an internal flow situation versus external flow situation. Do you have energy losses in external flows? Of course you do. So now when we're performing the energy analysis, we cannot assume that energy is constant. We will have energy losses. And so now what happens is, as we move, if we have a flow from left to right here, as we move through the system, the energy grade line must be decreasing in the direction of flow. We are losing energy as we move through the system. And if we've selected 2 points, 1 and 2, with the center line in this horizontal pipe construct, those 2 elevations in the center line of the pipe are all horizontal, so Z1 and Z2 are the same. We can measure from point 1, the total energy, B1, so this line is B1. We can measure from point 2 the total energy at B2, and then the difference between those 2 is the energy losses. And again, if all you had was pipe friction, in this case, all of your energy losses are due to frictional resistance, H sub F. Okay? And where we would use that, well, again, we have 2 different types of energy losses in systems. This lecture, next lecture, we're going to focus on friction resistance, but there are other locations where we get energy losses. We call those minor losses, and I described these last time. In fact, these first number of slides were all from the last lecture. So again, along a path line between any 2 points of an energy analysis, the total energy losses would be equal to the sum of friction losses plus the sum of minor losses. Again, that's along a path line, so that path line can go through different diameters of pipe, different pipe materials, different appurtenances like valves and other types of fittings. And when you go from point 1 on the path line to point 2 on the path line, the difference in the energy is the sum of all of those energy losses. In this case, there's no mechanical energy between points 1 and 2. We'll add that in later. So for just the friction loss term, the variables involved are the pipe diameter, the pipe length, the absolute roughness as it's known, and again, your book uses case of S, some other books use lowercase e, the fluid average velocity, the kinematic viscosity of the fluid, and those all lump together into what we call Darcy-Weisbach friction loss equation. So this is one of the numerous types of equations used for closed conduit flow. I will talk about one or two others. Darcy-Weisbach universally on this globe, this is what most people use because it's a much more accurate predictor than some of the other equations that are conventionally used even in our profession. So the old timers will use some of the other equations, and I will introduce you to them. They are in your book, just so that you will recognize them when you come across them. They're also in all the software programs. So for this friction loss equation, H sub F is the friction loss and has the dimensions of length because it fits right into the energy equation. F is the Darcy-Weisbach friction factor. L is the pipe length between the 2 points that you're doing the energy analysis between, points 1 and 2 on the previous slides. D is the pipe diameter, and remember, we'll ultimately need to talk about cases when the pipes aren't circular. So this is also adaptable to non-circular cross sections. Average velocity we talked about, and acceleration of gravity. So again, we have this Moody diagram. And again, it basically has, and this will be on a future slide, basically have 4 quote-unquote axes. The friction factor, the Reynolds number, the relative roughness, and Reynolds number times friction factor to 1/2. And what you see are these 4 axes, as I just identified. And for those 4 axes, there's basically 2 sets of contours. The blue contours are Darcy-Weisbach friction factor versus Reynolds number versus relative roughness. So there's, in the transition zone, again, that's referring to the characteristics of the boundary layer, so transitional boundary layer has a laminar sublayer. In the transition zone, you need both Reynolds number and relative roughness to find the friction factor because these contours are curving. And if you had, for example, a relative roughness of 0.005, it is visually between 0.004 and 0.006. And so what you would do is visually interpret between those 2 contours that are on the diagram between 0.004 and 0.006. In the turbulent boundary layer zone, all you need to know is Ks over D. And in the laminar zone, all you need to know is the Reynolds number. The other contours on there, on this diagram, are the black contours. And for the black contours, you're using the upper horizontal axis, and if you knew this quantity, REF to the 1/2, and I will be talking about it in a future lecture, these contours go diagonally from the upper left to the upper right, and again, you would need F versus REF to the 1/2. If you knew REF to the 1/2, you could solve for F. And that is actually convenient for one class of problems as we talk about them. So on this diagram, of the 4 axes or variables up above, if you know any 2 of them, you know the other 2. So if you knew Reynolds number in case of S over D, you know friction factor and REF to the 1/2. Again, if you plotted case of S over D of 0.005 with a Reynolds number of 2 times 10 to the 5th, you would go in at 2 times 10 to the 5th to where it crossed that intersection with the relative roughness, and then you would go horizontally over and read F, and you would go parallel to the contours of REF to the 1/2 to find the value of REF to the 1/2. That's not a common need to know, but that's how you use it. Again, if you know any two, you know the other two. So, the Moody diagram was one page of your handout. The other page of your handout were the different equations that are fitted to different pieces of the Moody diagram. And it's important to understand that many of the equations have caveats or ranges of variability. So for these ranges of variability, for example, you can only use the laminar equation when the Reynolds number is less than 2,000. You can only use these transition equations. Some of them are good for just knowing the Reynolds number. Other of them, you need to know both the Reynolds number and the relative roughness. And notice here, instead of case of S, E is used. Okay, not the end of the world. All right, so if you look at the names that are present on the very first column, on the next page is the Moody diagram. And if you go down the previous page from laminar, that's the first one, laminar to Frankel to Blasius to Colebrook, etc. Here's the laminar equation, and it's good in the laminar zone for Reynolds number less than 2,000. Swami and Jane, Holland, Colebrook are all good for the transition zone. I'm going to go back to the previous page. So Colebrook, Swami and Jane, Holland are good for the transition zone. That's what the second column is for on this page, full of equations. And again, most of these equations are in the textbook. And then in the turbulent zone, Swami and Jane von Karman. Again, you'll see those equations on the previous page. And then the most interesting one you should be aware of is what's called the smooth pipe curve. The smooth pipe curve is the lowest curve in the transition zone. And when you are on the smooth pipe curve, you never escape the transition boundary layer. If you, again, look, this dashed blue line is what divides on the right the turbulent boundary layer from the transitional. The smooth pipe curve can never get out of that zone. So you always have a transitional boundary layer. And there are 3 equations, Frankel, Blasius, Colebrook, that are specifically for the smooth pipe curve. And you will see some of your problems where they do not give you the material type. You might be on that smooth pipe curve, and I'll talk about that a little bit later. So just be aware that the equations on that handout are describing different zones on this same handout on the Moody diagram. And again, the Moody diagram and many of these equations are the standard of practice in our profession. So here's an example. We have a cast iron pipe, and in the future, I might just be writing CIP, cast iron pipe. It's got a diameter of 12 inches. It has a flow of 3,000 gallons per minute, and we have water at 50 degrees Fahrenheit. What's the Darcy-Weisbach friction factor F? So in this case, water at 50 degrees, we know what the, we know the kinematic viscosity, we know the diameter. If you go to the book will have this table right across the page from the Moody diagram. And for cast iron pipe, you see that we have an absolute roughness of 0.10 inches. And again, if I divide that by 12 inches per foot, I get 0.30833 feet. In the handout that I gave you, with the ones we were just looking at, in the lower left-hand side is a table that looks like this. Again, if you look at cast iron, you can see in this table, it has a absolute roughness, equivalent sand roughness as it's called, case of S, of 8.5 times 10 to the minus 4 feet. Okay, so that's the next one here, which is 0.00085 instead of the 0.000833 above. So these are book values. If you're actually designing something, what you typically do is contact the manufacturers who are making this product, and they will give you this information. That's the best source. When you're writing specifications for bid documents, you can identify the pipe from a specific manufacturer, and then you always say, or equivalent. So for example, ASTM Schedule F cast iron pipe from so-and-so, or equivalent. And that means it's going to have to meet this kind of performance specification. So now that we know the relative roughness, we can calculate, now that we know the absolute roughness, case of S, we can calculate the relative roughness, which is case of S over D. Case of S, absolute roughness, it has dimensions. Case of S over D, relative roughness, it's dimensionless. So 0.3085 feet divided by the diameter of 1 foot is 0.3085. You were given a discharge of 3,000 gallons per minute, and you know by now that there's 448.8 gallons per minute per cubic foot per second. 7.48 gallons per cubic foot and 60 seconds a minute. So if you divide 3,000 by 448.8, you get 6.68 cubic feet per second. The area of the cross section is pi over 4d squared, pi over 4 times 1 foot squared, 0.75 square feet. And therefore the velocity, the average velocity of the cross section is the discharge over area. Our discharge, 6.68 cubic feet per second, divided by the area, 0.785 square feet, is 8.51 foot per second. And now we can get the Reynolds number. The Reynolds number is the velocity times the diameter over the Carnot viscosity. And the Reynolds number we calculate to be 6.04 times 10 to the fifth. So remember, from those equations or the Moody diagram, we typically need case of S over D, and we need the Reynolds number. For the Moody diagram, depending on where you are, in the laminar, all you need to know is the Reynolds number. But right now, you don't know where you are, well, you should. You can only have the laminar conditions when you have a Reynolds number of 2,000 or less. Our Reynolds number is 6 times 10 to the fifth, so you know you're not laminar, right? So it's either transition or turbulent. You don't really know where it is until you look at the Moody diagram. So you're either going to need to know both relative roughness and Reynolds number, or maybe just relative roughness if you're out in the turbulent zone, where all the contours are horizontal. So here's the Moody diagram. And again, turbulent zone and transition are divided by this dashed blue line. So we know we have a relative roughness of 0.3085. That's going to be visually between 0.001 and 0.00308. And so we would follow those contours across from the right, and as they bend in transition, we would want to stay at the same distance visually in between those two. On the horizontal axis, we have a Reynolds number of 6.04 times 10 to the fifth. So we plot 6.04 times 10 to the fifth until we intersect the contour of case of S over D. And you will notice that this is in the transition zone. Write that down. These plot in the transition zone. And so then we can go horizontally over, and you would read a friction factor of 0.0195. I expect three-place accuracy on the friction factors, whether you read them or calculate them. I expect that. If it's 0.020, I want to see that O to the right of 2, three-place accuracy. Okay, so that's one way to get a friction factor. However, in this example, you have all those equations on the other side of the Moody diagram on your handout. We know that we have a relative roughness of 0.00085, and we have a Reynolds number of 6.04 times 10 to the 5th. So you could use all of those equations in the handout. That doesn't mean you're right, but you can certainly use them because all of those equations use Reynolds number and or relative roughness. So for example, we could actually calculate a Reynolds friction factor with the laminar equation, and you would get a friction factor of 0.30011. Is that what we read off the previous slide with the Moody diagram? Of course not. And that would be completely wrong because, again, if you use that equation, you would be taking that line of F is equal to 64 of the Reynolds number all the way out to 6.04 times 10 to the 5th. That's why you get such a small number. It's wrong because your Reynolds number is greater than 2,000, but for some reason that doesn't stop people from using equations if they're in front of them. So that's why it's really important to make sure you meet the constraints and the requirements or the range of validity when you're picking up these equations. So you shouldn't be using the laminar equation because the Reynolds number is not less than 2,000. I hope I've stressed that enough. Similarly, the next three equations, Prandtl, Blazes, Colebrook, are for the smooth pipe curve. I'm going to go back. The smooth pipe curve is down here. It's the lowest contour. We're on a contour that's doing something like this. Are we on the smooth pipe curve? No. So if we go to that next page, if we're trying to use these smooth pipes, this one we've met. The Reynolds number is greater than 4,000. This one we actually didn't need it. We're just outside of that one. And this one we've met it, but nowhere does it really say anything about the relative roughness other than this. This says K sub S over D is 0. Whenever you see smooth pipe, and if you're using that smooth pipe curve, your relative roughness is 0. And in our case, we have a relative roughness of 0.3085. That is not 0. So again, you can use those equations and you will get answers, and they're all less than the 0.0195 that we found. Why? Because the smooth pipe curve is so much lower than the curve with the contour with a relative roughness of 0.00085. So you're getting numbers when you use those equations, but again, you are using the wrong equation because you're not in the smooth pipe relationship. So these three relationships, Colebrook, Swami, and Jay and Holland, are all for the transition zone. That's exactly where we are in this problem. We're in the transition zone. And in that case, they should all be giving answers very similar to what we read off of the Moody diagram. So remember, we read 0.0195, and all three of those are very, very close to that. And I would take one of these equations better than my tired old eyeballs and reading off the Moody diagram. And then lastly, you can, of course, use an equation for the turbulent boundary layer. And again, you're on the Moody diagram, and your contour of relative roughness, 0.00085, is in the transition zone. And that will give you a friction factor higher than that plateau. Remember, the plateau is that portion of the contour for K sub S over D that's in the turbulent zone and it's horizontal. And so you would expect the von Karman equation to give you something less than what we found off the Moody diagram, 0.095, because again, in this case, for von Karman, it's giving you a description of the size of the laminar sublayer. That's what delta prime is, remember, from the outer layer theory. You could actually calculate that and you would see that you were out of spec for that. So again, the equations will give you a good answer, but you have to make sure you use the right equation. More often than not, this is the one I personally use. If you look at the Colebrook equation, you have friction factor on both sides. In fact, you see REF to the 1/2 over on the right-hand side, and that was one of the axes on the Moody diagram, the upper horizontal axis. That makes the Colebrook equation difficult to use, just like Prandtl's equation is difficult to use. When F is on the two sides of the equation, it's a trial and error solution. So I typically don't use either of those because I'm not a big fan of trial and error when another equation is going to give me a good answer. But also I see more and more in this country, people are using Swami and Jane. And actually, it gives you a good answer out in the turbulent zone because it ends out in the turbulent zone. And once you're at the turbulent transition boundary, the friction factor contour is horizontal. So I'll even use that out into the turbulent. Okay, I think I've beaten that dead horse with a dead stick. So for closed conduit flow, this is how we calculate energy losses, or energy losses due to friction specifically. And for that equation, when we dissect it, we can see all of these different variables either obvious in that equation or buried somewhere then in that equation. So H sub F, L, D, velocity G, they're all obvious in that equation. Whereas the kinematic viscosity and the absolute roughness are buried in the friction factor. And to find the friction factor, you need that relative roughness and the kinematic viscosity to get the relative roughness and the Reynolds number. And then in addition, to get the velocity, you would use continuity, Q over A. And again, don't forget, kinematic viscosity is viscosity divided by density. And why I bring that up to you is because sometimes if you're using some odd fluid, if you go to an industrial handbook or a chemical handbook, you might get the viscosity and the density, but they may not be reporting the kinematic viscosity. So you should always be able to find kinematic viscosity if you know the other fluid properties. So how do we utilize the Darcy-Weisbach equation and energy losses in general? In design, we typically need to size the pipes. That is, what's the diameter? Very often in design, you have two locations. One might be where water is coming from, the source, and the other location is where water is going to, or any other fluid. And that's going to be the sink. That could be the point of use. So for example, it could go from the water treatment plant right to your faucet. So in between, there are an infinite number of ways to go. The shortest distance between 2 points is, of course, a straight line, but not all pipes can necessarily go in a straight line, especially in a big distribution system. So the length of the pipe, of course, is certainly in your purview, but very often we're looking at the diameter and then the material, case of S. That's something you will specify. You have to understand that in this type of analysis, we have continuity and energy. Those by and of themselves will not be able to solve all of our problems. We use the Moody diagram or the equations describing the Moody diagram to give us another boundary condition to help us solve those problems. But even then, we may have more variables than we have equations. So in the process of design, very often we select variables. For example, I'm going to use cast iron pipe. And then we go through the design and see if everything works. If it doesn't work, then we have to redesign. Design is an iterative process. You don't guess at the answer right away because you have too many variables, too many design variables. The other thing we could be doing in design is we could be sizing a pump for the pump power, which directly translates to the pump energy. Remember, power is equal to the flow times the specific weight times EP over a conversion factor. And the other thing for system performance we might be trying to design is a specific head loss or keeping this head loss to within a certain amount. So those are all design types of problems, and this is where, again, calculating friction losses or energy losses in general will come in. For analysis, again, think of a pressure distribution system versus mostly what we'll do in here. In this class, you'll have very simple systems. Go from this reservoir to this reservoir, and we're going to have this pipe in between. Very simple systems. But in pressure distribution systems, you have multiple pathways, multiple pipes. And one of the things we may be after is what's the flow distribution. The second might be the pressure distribution. And the last associated with the pressure distribution is the energy loss distribution. So in distribution systems, the energy grade line is now a surface over the system. The hydraulic grade line is a surface over the system. And I think you're very, very familiar with these concepts. So, there it is. So on the right is a topographic map over in Vermont. And on this topographic map, I think it should be obvious to you, it says Katy Hill here, but if you didn't have that name Katy Hill, you should see that the contours go from 1,000 here, 900 here, and then at the very top it's 1122. So you know you're going uphill. The topographic map is really a direct analogy to the energy grade line over a distribution system. You know where the locations of highest energy are, and those are typically the source locations. So that's either where you have a pumping station or a reservoir, tank. The other thing you can identify is where the elevation contours are spread far apart. That's a very flat slope compared to where the contours are very close together. You recognize that as a steep slope. And again, if the topography or the topographic contours are a direct analogy to the energy grade line, where we see the energy grade line far apart, we know we have a flatter energy grade line, and therefore we don't have as many slopes. So here's the pipe, flows in the pipe, and we see a flat energy grade line compared to over here, where we have the pipe again, and now we have a very steep AGL. And so ultimately, and this is of course, we're offering next semester, design and pressure transmission systems. When we look at distribution systems, ultimately we look especially at this, because if you're trying to improve performance, obviously where you're losing a lot of energy are places where you can improve performance, either by putting siblings, another pipe right next to the existing pipe, or replacing the old pipe with a newer pipe, or swabbing out that pipe, pigging as it's known. You clean out the pipe to make it smoother because you may have tuberculations or growth inside of the pipe. And I'll bring in some cross sections of pipe so you can see what they look like after a few years of service in the local system. So, three fundamental types of closed conduit problems. The first class, or the first type, is to compute the energy losses. The second is to compute the discharge. And the third is to compute the diameter. We're going to be doing examples of each one of these, and you're going to have homework problems on each one of these. The first one is always a direct solution. The second two may be a direct solution or trial and error, and that's what we need to discuss. There are a lot of ways of attacking these. Any more, you can make them direct solutions by using the equations on your handout, the equations that describe the movie diagram. So here's our energy analysis. This is the same slide as before. And whether it's the problem for H sub F, or the problem for discharge, or the problem for diameter, the pipe sizing problem, the exact same analysis is employed, the exact same equation. What we will be doing is creating or performing an energy analysis between 2 points. So, in the last figure, we had a horizontal pipe. The center line of the pipe is horizontal, and if we picked points on the center line, Z1 and Z2 are the same elevation. We have a constant discharge. In this course, that's what we're going to focus on, constant discharge system. That's steady state, as it's called. We're going to have, in that last figure, we have a horizontal pipe with a constant diameter. If the diameter is constant, then the velocities are constant because the area is constant and the discharge is constant. And so when you take your energy equation, since the velocity heads are the same and the elevations are the same, what you're left with is that the difference in pressure between the upstream point and the downstream point is the friction loss or the energy loss. And that energy loss is the Darcy-Weisbach equation. Okay. So, KS, be careful. In some problems, if a material is not stated in the problem, and the problem says smooth pipe, if the Reynolds number is less than 2,000, the friction factor is always 64 over the Reynolds number. It doesn't even need to say that the pipe is smooth. If it just gives you a problem and there's no material specified and it doesn't say smooth pipe, calculate the Reynolds number first. If the Reynolds number is greater than 2,000, and in the problem it says smooth pipe, then you use the smooth pipe curves or relationships, either from the Moody diagram, the curve, smooth pipe curve, or those three relationships that were built around that smooth pipe. And remember, for the smooth pipe curve, the case of S over D is 0. That's what it's indicating. For laminar flow, when the Reynolds number is less than 2,000, we know that the friction loss is the Darcy-Weisbach equation. Darcy-Weisbach equation, DW. We also know that the friction factor is 64 over the Reynolds number, which is 64 times mu divided by the velocity times the diameter. And so we can make this substitution into this Darcy-Weisbach equation, and what you would get is that the friction factor is 32 mu LV over GD squared. Again, if you are not told what the material is, and you're not told it's smooth pipe, if you calculate the Reynolds number and see that the Reynolds number is less than 2,000, you can directly calculate the friction loss. You don't need K sub S. It does not appear in this equation because it's laminar. All the data collapses onto the laminar line in the laminar zone of the Moody diagram. So, here's the second problem for today. 4 more slides. In a pipe, carbon tetrachloride, temperature is 40 degrees Fahrenheit, that helps me find fluid properties, is flowing at a discharge of 280 gallons per minute. Again, there's 3 classes of problems, H sub F, Q, and D. Next week, we're going to talk about Q and D. Today, we're talking about H sub F. So we have 280 gallons per minute of carbon tetrachloride flowing in a 4-inch diameter CIP, cast iron pipe. What is the pressure drop in 40 feet of horizontal pipe? So as we indicated on previous slides, for a horizontal pipe, we select 2 points, point 1 and point 2 on the center line. We know that constant diameter, constant flow, the 2 velocities are the same, the 2 elevations are the same, and what we would get is that the friction loss is the change in pressure over gamma. This is what we derived on the previous slide. Upstream pressure minus downstream pressure divided by gamma. And that H sub F is always equal to the Darcy-Weisbach statement, FL over dV squared over 2G. This question asks for the pressure drop. P1 minus P2 is delta P. That's what the question is asking for. So if we can calculate Darcy-Weisbach friction loss, we would just multiply it by the specific weight of carbon tetrachloride to get the pressure drop. So, kinematic viscosity of carbon tetrachloride, 5.6 times 10 to the minus 6 foot squared per second. The specific gravity of carbon tetrachloride is 1.59. I couldn't find the specific weight of carbon tetrachloride. In the back of your book, I believe they have it at 68 degrees Fahrenheit. So with the specific gravity, I know that the specific weight of carbon tetrachloride is the specific gravity of carbon tetrachloride times the specific weight of water. And that gives me 99.2 pounds per cubic foot. The length is given in the problem. The distance between the 2 points is 40 feet. The pipe diameter is 4 inches, which is 0.333 feet. Acceleration due to gravity, BGS system. Discharge is 280 gallons per minute, which is 0.624 cubic feet per second. Cross-sectional area, pi over 4d squared, and that allows me to calculate the velocity of 7.15 feet per second. So again, we're just synthesizing data. What we want to do, we now know the length, 40 feet, we know the diameter, we know gravity, we know velocity. To find the friction factor, we need Reynolds number and case of S over D. And then we can calculate delta P over gamma, and we know gamma. So, Reynolds number, velocity times diameter over kinematic viscosity. You have the velocity, the kinematic viscosity, and the diameter on the left-hand side. That computes to be a Reynolds number of 4.25 times 10 to the 5th. Relative roughness is the absolute roughness cast iron pipe. I didn't put it on here, but it's the same as the last problem. .3085 feet. So case of S over D, 0.3085 feet divided by 0.333 feet is a relative roughness of 0.00255. So now you have the two terms we need to find the friction factor. So we can go right to the Moody diagram, just as we did before. On the Moody diagram, we have a relative roughness of 0.00255. So we have one contour of 0.002, another contour of 0.304, and visually it's probably just above this horizontal line. And it starts to curve. And then we have a Reynolds number of 4.25 times 10 to the 5th. And it's very, very close to the turbulent, but it looks like it's in the transition zone. We go horizontally over from where those two intersect. Again, where relative roughness, even where it's curving, intersects with the Reynolds number, you go horizontally over from their intersection to get the friction factor. And you can see a friction factor of about 0.0255. You can clearly read the horizontal line for 0.025, above it is 0.03, and every division is a 0.001 change in the friction factor. So between 0.025 and 0.026, it looks like it's midway between, so that's 0.0255. Again, visually, you need to read that third, the very last place to make sure that the third place is very good. So, from the Moody diagram, we just read that the friction factor is 0.0255, but it seems to be very close to the transition turbulent. It seems to be in the transition zone. So you can use any of the equations in the transition zone, and they should give you the same thing you read off the Moody diagram. So if we use the Swami and Jain equation, 0.0256, Holland, 0.0254, and the Moody diagram is right between those two. Any one of those three is acceptable. My opinion to you is if you're using the Moody diagram, I think you should check it just to make sure you didn't screw something up on the Reynolds number or case of S over D, reading the Moody diagram. So now that we have a friction factor, we can finish the problem and calculate the friction loss. Once we have the friction loss, we know that's the change in pressure over specific weight. So the change in pressure, we can multiply the specific weight times the friction loss of 2.43 feet, and we see that the pressure drop would be 1.67 pounds per square inch in this case. So, I'm right at noon. Are there any questions on this? Because you should expect to see an homework problem on it. I know you're taking off for vacation, or you may already be somewhere, but I think you're going to need something to do between now and Monday, so I will be giving you homework. No questions? All right. Then make sure to commit the sin of gluttony over the next few days. And enjoy your break.